So I think we can start, and if some more people will join, I will take care of this.
All right, thanks, Linda. Okay, so welcome everybody to the diffusion seminar again after a break over Christmas. We have got a set of very interesting speakers lined up again, and we have two people joining us today who got up early to do so. So we have Corliss CEO, who's in Toronto, and I'll introduce her in a minute. And the second talk will be by William Nelson from Hawaii, where it's really, really early, and thank him for getting up at this hour to do this. So before we get started on that, I'd just like to make an sort of an announcement, if you will, that we have a web page now called DiffCron. I'll try to go there in a minute. And let me see if I can share my, oh, so the other, okay, so I won't interrupt Corliss sharing her screen right now because that should work. But maybe later on, I'll show you my screen. But what I wanted to announce was that we have a web page called DiffCron, and I'll put the link on the chat maybe later, where we're trying to put together all kinds of resources for people who work on these kinds of things. So among other things, if there are programs available that people can use, we are sort of putting a link so a user can go there and look up what kind of programs are available and get the links to go to those programs and use them. So if you have something that's there you'd like to put up there, please let me know if you have a web page or if you just have a program that you would like us to put up on the server, we'd be happy to do that. So that's one thing that I wanted to let you know. And the other thing is that we are also trying to put together a site where you can go in and look up what publications are around. So the two kinds of questions we get very often are, what is the diffusion coefficient of X, Y, and Z in mineral X, Y, and Z? And a lot of it, whatever was around at the time, got very nicely summed up in the Reviews in Mineralogy and Geochemistry volume that came out in 2010. But things have been coming out since then, which is good news. And so we're trying to sort of have a web page where anything we know of would be available. We're also sort of putting in papers that are using diffusion modeling to get timescales on the web page. So if you have any of those, either one of those, please let us know. And also please make use of the resources. And if you have any problems or feedback, do let us know about that. Okay. So with that, I'd like to go to the speakers. So our first speaker is Corliss CEO, and I can get her CV up. Yeah. So Corliss did her PhD in University of Chicago in 2014, and that's when she began working on looking at isotopic fractionation during diffusion. So conventionally, we've been raised to believe that things like iron and magnesium do not show isotopic fractionation easily, and that's been shown to be not the case. And along with some people in Hanover, Corliss was one of the first people to show that effect and show how that can be used in diffusion, and she'll be talking more about it today. But after a PhD in Chicago, she was a postdoc at Carnegie for 2 years, where she continued working on diffusion, actually doing some experiments and things. And this was followed by quite a long stretch as first a postdoc and then a staff scientist at the Lawrence Livermore Laboratories. And very recently, just last year, she moved to Toronto on a faculty position. So and we was just talking to her before this today, and I found out that she's planning to get back to doing more of the diffusion stuff, which we are, of course, all very looking forward to. So with that, I would let Corliss take over here. And, well, I'm sorry. So the one thing I should have said at the beginning was So the way we do these talks are, we have 2 talks, 30 minutes each. After the talk, we have a few questions. But then after the second talk, we come back and take questions on both of the talks. So if you have questions or comments that doesn't get answered in the first round, please, just keep sending them in the chat, or you can speak up and we'll take on those. We like to take time and make sure we have discussion. That's the point of these seminars. Okay, so sorry for interrupting it. Corliss, now you're all yours.
Hi, everyone. Good morning, good afternoon, good evening. Thanks for coming to this talk. I'll be talking about crystal growth or chemical diffusion, stable isotope diagnosis. So basically, it's application of stable isotopes to discern whether it's crystal growth or chemical diffusion that's generating chemical zoning in minerals. So these are, today I'll be focusing on olivine, and these are images that we're all familiar with, a zoned mineral and with gradient in MgFe. And a question that we always ask ourselves is, are these really diffusion profiles? And if they are, then you can do diffusion modeling to retrieve the timescale between magma mixing and eruption, for instance, and so forth. But besides answering the question of whether something is crystal growth or diffusion generated zoning, you also have to ask ourselves, what is the boundary condition and initial condition that we will use to model these profiles? And that's because the calculated diffusion timescales relies heavily on the choice of modeling parameters. So in the next few slides, I will show you an example of how we can model one single chemical profile. So shown here is an example of olivine zoning going from 0 at the rim to 600 micron at the core. So this is data that's taken from Uza et al. 2015. So plotted on the y-axis is FO number. So the first way that I would model this is to assume that this crystal has been submerged in a melt that is out of equilibrium with a melt that is more iron rich. So in an effort to re-equilibrate, iron will diffuse in while magnesium diffuses out to generate a zoning profile. And the boundary condition that I've imposed in this scenario is a fixed equilibrium rim composition in the olivine since the onset of diffusion. So the equilibrium value is fixed here, and just run the diffusion model until I get a fit that is fitting to the data. And so in this instance, there's no crystal growth, it's just diffusion. And the second way that we can model such a profile that it's also diffusion only and without crystal growth is if I assume a different boundary condition. So in this instance, the melt composition is evolving from magnesium rich to iron rich with time. So this is a case scenario where you have a crystal that's trying to constantly re-equilibrate with the melt that it's grown in. But that melt is getting more and more iron rich with cooling of the magma. So if I apply this boundary condition to an initially homogeneous crystal and run the diffusion profile, run the diffusion model, I also get a very nice fit to the data. And the third way that I could model this is kind of the same as scenario 1, where I put a crystal in a melt that is more iron rich than what's in equilibrium with the olivine, with this existing olivine. So in this case, instead of no crystal growth, I'm growing the crystal at a constant rate. So here I've marked a boundary where the initial crystal is to the right of the gray dashed line, and the new growth is to the left of it. So this is a model of simultaneous diffusion and crystal growth in a melt of a fixed composition. So if I let the diffusion model run and the crystal growing at the same time, then I also get a very nice fit. And the last way that I'm showing today for which I can model this profile is to have, again, scenario 1, but with crystal growth. So this crystal, instead of, comparing to scenario 3 where it's growing constantly, this crystal has grown instantaneously, a mantle surrounding the original crystal. And so you have an initial profile. This is an instantaneous growth on the rim of the crystal. So you have an initial profile that's marked by this dashed red step function. And this crystal is trying to relax this initial profile at the same time that is exchanging chemically with the melt surrounding it. So in this case, I also get a very nice fit. So there are at least 4 different ways in which you can model and fit a single chemical profile. And the calculated timescales between these models, they differ by a factor of 10 at least. But how do we know which is the right one to use? What are the right modeling parameters to use? So this question of what boundary conditions to use and how much crystal growth is there, how much diffusion is there, it has really, these questions have been around for a long time. And how do we go about addressing that? So in 2010, Fanjun Tang et al. Published a paper that showed the discovery of negative correlation of magnesium and iron isotopes in olivines. So isotope data, they are reported in delta notation. On the y-axis, I plotted del 56 iron. The definition is given on the left here. It's the relative difference in the 56/54 ratio in the sample to a isotopic standard, and multiplied that by 1,000. Whereas for magnesium data, we'll be plotting del 26 magnesium, and that is just the 26/24 ratio in the sample relative to a standard. And that relative difference is divided by a factor of, is multiplied by a factor of 1,000. And in the background here, you see data for oceanic basalt. So it is for del 56 iron that plots close to 0, which means that oceanic basalt have a isotope composition that is close to the standard that we all use. And anything that plots above this gray area, it's isotopically heavy compared to the standard and the basalt. And anything that plots below, so in the negative region, that's isotopically light in iron. So for magnesium, there's a little bit bigger spread in oceanic basalt, and they fall in the negative region, and that's just because oceanic basalt have a different isotope composition compared to the standard that we use. That's okay, but anything to the right would be isotopically heavy in magnesium. It's going towards a more positive number. Anything to the left is isotopically light. So what we see here is that oceanic basalt, they don't really show large fractionation, at least in iron isotopes. And that's because in magmatic systems where temperatures are very high, isotope fractionation tends to go to 0 in equilibrium processes. And so this discovery of very, very large fractionation of more than 1 per mil in iron and about 0.5 per mil in magnesium, it's striking because we always, like Shumit said, we tend to think that at high temperature, things don't fractionate much, but this large fractionation is due to kinetic processes. It's not due to equilibrium processes. And the way to generate such a negative correlation in these olivines, so sorry, I forgot to mention that each point is olivine fragment picked out from Hawaiian basalt. So the only way to generate this negative correlation in olivine is by chemical diffusion. So here on the left, I've shown a cartoon where you have an olivine that is trying to re-equilibrate with a melt that it's out of equilibrium with. And here it shows a case of normal zoning where iron diffuse into the olivine, magnesium diffuse out of the olivine. So they interdiffuse in order to reach re-equilibration. So in this case, the light isotopes always diffuse faster than the heavier counterpart. So for iron 54, the light one, would have diffused much farther into the crystal than iron 56 would have. So what you have in your crystal is basically a collection of light isotopes of iron. So that explains why things are in the negative iron isotope region. And at the same time that iron is diffusing in, magnesium has to get out of the olivine crystal. And again, the light isotope can get out faster than the heavier one. So what you're left with is an isotopically heavy olivine in magnesium. So that explains this region, the lower right-hand region of this plot. So if you have reverse zoning, iron will diffuse out, magnesium diffuse in. So that would be the opposite. That would explains the upper left-hand region of this correlation. So to get a negative correlation in olivine crystal, diffusion is responsible. And to put it another way, if diffusion controls the chemical zoning in your olivine, you would see this negative correlation. And we'll come back to this in a few minutes to show that this correlation holds up for intragrain analyses as well as bulk olivine analyses. So now going back to this question of what is the right model to use to model this crystal. Now we can see how isotope can help us now that we know that isotopes, they're very sensitive to diffusive processes. So to model the isotope profile, we need an extra parameter, which is beta in this equation. So it describes how fast the light isotopes diffuse relative to the heavy isotope. So this is the ratio of the D's on the left side of the diffusion coefficient. And that ratio is inversely correlated to the inverse masses raised to the beta exponent. And it's important to use the right beta because beta has a big effect on the resulting fractionation from your model, as beta scales linearly with isotope fractionation. So in diffusion experiments that I've done, 2018, determined that beta has a value of around 0.16 in olivine for iron. So to model these isotope profiles, I would use a diffusion coefficient for interdiffusion magnesium and iron and use that as the diffusion rate for the heavy isotope, so 56 iron, and model the 56 profile using that D. And then I would use beta to calculate the diffusivity for the light isotope, which is in our case, iron 54. And I go ahead and model a separate profile that describes iron 54. So now I have two profile, one for 56, one for 54. And I just ratio the two, get their relative difference and multiply by a factor of 1,000. So that gets me the isotope profile. Okay. So now on this slide, I show the associated isotope profiles with all of these different models. So what you can see here is that while all of the chemical models can fit the actual data, and they all look very similar, their associated isotope profile, they look very different. So let's go through each one of them to find out why they are very different. For the first case scenario, where we have an initially homogeneous olivine submerged into a well-mixed melt, you have a constant boundary condition. The rim, it's always very iron-rich, FO77. So in this case, you have the largest diffusive flux, which results in the largest isotope fractionation, more than 3 per mil here. In the second case, in the second model, you have this initially homogeneous olivine that is trying to re-equilibrate in an evolving melt that is progressively getting more iron-rich with time. So in this case, you have a smaller diffusive flux, especially at the beginning. And we require a longer diffusion timescale to model this chemical profile. And you see that the penetration for iron isotope it's also farther into the crystal than compared to the case where you have a fixed boundary condition. And now to the third model, where you have crystal growing accompanying chemical diffusion. And in this case, you have almost no isotope fractionation. And that is because at magmatic temperature, you don't have any equilibrium fractionation between the olivine and the melt. So as the crystal is growing, the crystal incorporates unfractionated materials, and that unfractionated material dilutes all the diffusive signal. So that's why it has the least isotope fractionation. And then the last model, where we're modeling an instantaneous growth of olivine surrounding the initial crystal, we also have less isotope fractionation compared to the first case of fixed boundary. And that's because this mantle is very iron-rich, it's unfractionated. So this iron-rich mantle also dilutes diffusive signal. So that's why we have a very similar shape to the first model, but the fractionation is smaller because of that dilution of the unfractionated iron-rich mantle. So now we know why we have the magnitude of fractionation and the shape of these profile. Let's plot the actual data collected by Uza 2015. So these are the actual iron isotope data that corresponds to the chemical profile, the actual chemical profile shown in the middle panel. In this data set, the isotope fractionation, the isotope error bars, they're smaller than the sizes of the simples. And what we see very clearly is that the first model, it doesn't fit the isotope profile. So we know that this is not how we should model the olivine. And the second one fits very well. So it is the best fit. So this is likely the correct way to model the olivine. And the third one, it doesn't fit at all. And the fourth one, it fits okay, but not as well as the second one. And now let's look at the magnesium associated with the same profile. So iron isotope, it has light composition, because again, the light isotope diffuse into the farther into the crystal. And so you're left with heavy magnesium isotope correspondingly, because they interdiffuse. So here you have heavy magnesium isotope composition, and the fractionation is actually small compared to iron. It's about 1/10 of that compared to iron. And that's why magnesium, it's not very good for distinguishing between different models, So for magnesium, model 2 and model 4, they look very similar. Both are equally good fits. And that's because magnesium, they show less fractionation in magnesium-rich olivines due to the high background of unfractionated magnesium. So here we're modeling a crystal that's around, that's between FO77 and FO91. So this olivine has a lot of unfractionated magnesium to begin with, and that just dilutes the isotope fractionation signal. So iron is gives better constraint to the modeling parameters. So if I plot the iron isotope and the magnesium isotope on the same plot, and the best fit models, this is how it looks. The center of the crystal, things are not fractionated because at equilibrium, there's very little fractionation at high temperature, and the rim is also not fractionated, and that's because the rim of the crystal is in equilibrium with the surrounding melt. So you see the same isotope composition as you would in the core of the crystal, and all the diffusive signal, it's in the interior. So now, if we plot the isotopes against one another, we see the same negative correlation that we saw for the olivine fragments studied by Tang et al. 2010. So this negative correlation holds up whether you have reverse zoning or normal zoning. As long as you have interdiffusion of magnesium iron, you have a negative correlation. And the boundary condition and the crystal growth rates, it doesn't really affect the direction of correlation. You would always get a negative correlation if you have magnesium iron interdiffusion. So knowing this, we can try and make use of this negative correlation and answer the question, do zoned olivine generally show negatively coupled magnesium iron isotopes? A different way of asking this question is diffusion generally responsible for generating zoning in olivines? So this grain that I've studied in 2013, an olivine from Kilauea Lake, Hawaii, show this negative correlation. So in this case, yes, diffusion is responsible for generating zoning in the olivine studied. And here is a different set of samples studied by Uza et al. 2015. And this, these are sampled from Central and Canary Islands. So shown here are 8 different olivine crystals. And so you have iron isotope on the y-axis, magnesium on the x. This is a beautiful negative correlation, and that's indicative of iron magnesium interdiffusion and generating zoning in this olivine. Another big, beautiful correlation to the right and to the right of that again. But you do see instances where you don't see a negative correlation, or you see, interestingly, 2 different correlations. One is flat line and another one is a negative correlation. So this is interesting in that either the history of this crystal is more complex, or magnesium iron interdiffusion is not responsible in generating chemical zoning. So these are not really suitable for diffusion chronometry. Definitely this one at the bottom. And then now another set of data from Corliss et al. 2017, looking at olivines in Martian sugartite. And again, you see some, negative correlation. There's not enough data point in between, but you could argue for a negative correlation here and there. But for some crystals, for sure, I don't think we can make an argument for a negative correlation in these cases. So these are also crystals that are not suitable for use for diffusion chronometry. And these all have normal zoning associated with these isotope data. So moving on to another paper by Uza, 2018. It's olivines from volcano in Costa Rica, where each panel, again, is a different crystal, where you sometimes see nice correlation, but sometimes no correlation or even slightly positive correlation. So in this case, 3 of these grains are, again, show more complex history, or they may just not be suitable for diffusion chronometry purposes. So the bottom line is that from all the data that's been studied by Stefan Weyer's group, Mānoa and Collinet and myself, we have shown that not all zoned olivines show evidence of magnesium iron interdiffusion. And so if modeling, diffusion modeling was applied to chemical profiles inherited during crystal growth, then the result would be erroneous. Then you're modeling, basically applying a diffusion model to a grain that inherited its zoning from crystal growth. So we should all really use this isotope toolbox to select the useful crystal for diffusion chronometry. But another question is, well, can these isotope analyses be done routinely? And the answer is yes, these analyses can be done routinely. So shown here, it's the isotope profile for the same olivine crystal that I've studied from Kealoiiki lava lake. So iron isotope on the x-axis and distance against distance. So 3 sets of data are plotted here. One is micro drilling, where you use a dental drill bit to drill into the crystal, digest the powders, do column chemistry to purify iron. And then I measure the iron isotope composition on MCSE-PMS. So that set of data is shown in blue. And then the same crystal was also analyzed using laser ablation MCSE-PMS. So these error bars, they're 1 SD. So that is the red diamonds. And the green data points, they are measured using 1280 SIMS, a multi-collector SIMS. So it has the largest error bar because the matrix effect was the largest in SIMS. So the choice of technique, you have 3 different techniques that can do these measurements. And the choice of techniques depends on your expected fractionation and your sample size. So here I've plotted 2 SD precision on Del56 iron versus mask required or excavated during the analyses. So microdrilling, because you're purifying the solution so that it contains iron only, you have no interferences, no matrix effect whatsoever. It'll give you the best data. And followed by laser ablation, MCSE-PMS, and SIMS, while it has the best depth resolution, it doesn't have the best precision. So it depends on what you're looking for in your measurement. And how do we calculate the expected fractionation? Well, this is a general kind of idea to remember is if you have a larger core to rim concentration contrast, the larger isotope fractionation. So this is not minus, this is core to rim concentration contrast. So you can look at it as a ratio. So for the red curve, where you have a larger concentration contrast between the core of the crystal and the rim of the crystal, you get larger isotope fractionation, again, due to larger diffusive flux. And you have a smaller concentration difference between the core of your crystal and the rim of your crystal, such as denoted by this green model curve, you get smaller isotope fractionation just because of the smaller diffusive flux. So these modelings are helpful to do to try and see if the technique that you're after will be able to resolve the expected fractionation. And another thing to that you can model is the time evolution of the crystal. So shown on the upper panel here is a chemical profile. This is non-dimensional distance going from rim plotted to rim on the two ends. So in this case, the rim composition is 1.5 times higher than the core composition, the rim equilibrium composition. So initially, your crystal has a C to C naught ratio of 1. So that is just shows the crystal is initially homogeneous. And when the crystal is fully re-equilibrated, it'll have a concentration ratio of 1.5 compared to what it began with. So here you can see the time evolution on the upper panel for the chemical profile. Tau is the dimensionless time, which is radius square divided by diffusivity. So as you increase the time, you get this sort of approach to equilibrium. And looking downward here is a panel that shows the associated isotope profiles. So what you see here is that as you increase time, as diffusion propagates into the crystal, your isotope fractionation increases and is maximum at a point where you're halfway between your original value and the equilibrium value. So the start and the end result. If you're halfway through achieving that equilibrium core composition, then you have a maximum fractionation. So fractionation increases with time, and then it decreases. So it's also useful to know, whether you should, be picking crystal for which diffusion has affected the core, because that will give you the largest fractionation to measure. So in summary, diffusive transport generates large isotope fractionation, much more than equilibrium fractionation at high temperature. And magnesium iron interdiffusion results in negatively coupled magnesium iron isotopes. And of the 25 crystals that I'm showing you, 30% of them did not show a negative magnesium and iron isotope correlation, despite showing FO number zoning. So therefore, isotope analyses are needed to select the right crystal for diffusion chronometry, and they're invaluable in pinning down the thermal and crystallization histories in magnetic bodies. And lastly, just want to say that these are analyses, they can be done routinely, and it'll be a nice feature if we can use these isotope analyses as a routine tool in diffusion chronometry. So thank you for your time. I guess I'll take questions after the second talk, or.
No, thank you, Corliss.
Yeah.
So we will take a few questions now. So yeah, it was a very lucid illustration of what isotopic analysis can do and how it can help. And I thought it was very important that you showed that you can fit a profile even though you don't have any diffusion going on by a diffusion profile. So it's important to find tools that help you to tell apart crystal growth from diffusion. And this isotopic analysis is certainly a very powerful way to go about doing that. And it's good to see that it's more accessible than people might want to believe. So that's very good news. So let's see if there are any questions. I see there's a comment on the chat from Igor. Now, Igor, do you want to speak up and ask the question or comment?
Yes, I can. I mean, my first remark was I was sort of worried why the diffusion of the observed crystals in the Hawaiʻi sample we're going towards higher isotope fractionation of the iron. One of the very first slide. Thank you, Corliss. That's the one. Yeah. So how do you get the black squares? And possibly that would be in your fourth model, where you have a accreted rim, which has iron with a fractionation, with a delta of 0. And then you start diffusing that iron from the rim into the core, and thereby you would get a positive, a heavier delta 56.
Yes, you would. If the mantle is big enough, yes, you definitely would. In this case, here, the mantle, it's in communication with the melt. So I also fixed the boundary at the rim of the mantle right here at 0. So that's a fixed boundary condition. So you have an infinite reservoir of iron diffusing in from the melt. And so that's why you don't see the positive.
Your fourth model would explain that. And the other comment or question that I asked was, you measure majors like iron and magnesium, which is of course the obvious choice, but there must be some trace element like maybe nickel or cobalt, which is in disequilibrium between mantle and core. So
you're talking about trace element measurement or isotope measurements of
trace element to begin with, and then you can do isotopes on nickel, but not on cobalt, of course.
Yeah. So trace elements, they are affected by what else is crystallizing in the system while diffusion or growth is going on in the olivine. So the boundary condition can be a little bit more tricky to deal with trace elements. And so I've looked at trace elements of chromium, nickel, and aluminum. They're not straightforward to interpret.
Okay. Okay, thanks.
Yeah. Thank you.
I mean, I don't know about these samples, but when you do these models, usually you have profiles of nickel, manganese, and calcium as well. And I have no idea what isotopes do there. Probably also something. I don't know if anybody has looked at it. That'd be something to look at as well, I think.
It would be limited. The precision will be limited by the concentration. So
right.
Low concentration, yeah.
Mm-hmm.
Yeah.
So I see a comment from Stefan. So maybe, Stefan, do you want to just speak up and say that, or want to have everybody read it?
Yeah, it was just a comment that I would assume actually that just the extent of isotope fractionation is also already a measure if this is diffusion related or not. Nature is quite often complex, and you may have 2 or 3 different processes involved. That means at the end you likely can't model it anymore, but still large isotope fractionation may be preserved. Maybe the correlation or the anti-correlation is not preserved anymore because of this mixture of processes. But if you have such a large isotope fractionation, and we are talking here about the salts, let's say, equilibrium isotope fractionation should be so small. If you have large isotope fractionation of more than half a mil, it must actually be related to diffusion. It's not of use anymore. Your message is still correct. You can't use it for simple modeling. You cannot apply a simple model, but it still tells you it's a diffusion signature, let's say.
Yes, and if you have diffusion limited growth, that also imparts a chemical profile, but with not that imparts isotope fractionation, but not a negative signature. So you do, yeah, you have different processes that's all diffusion controlled, that will give you these large fractionation. But the but we have to know that those complex processes are going on, and not model them as a simple diffusion profile. Yes.
And there's a comment on chat from Philip, agrees and adds one more dimension to it, that it's becoming increasingly concerned that olivine growth may not be just concentric shells. So that's one more twist that comes to it. But you know, I mean, as we look more, we find more twists, but we're also finding more tools to deal with them. So that's the fun part of it. So I think I'll stop at that point with Corliss, but we can, you know, keep coming, the questions coming. We will come back and discuss more of this with Corliss, but now we can move to the second talk to get that in as well. So the second talk is by William Nelson from University of Hawaii at Mānoa. And he's going to talk about diffusion chronometry reveals rapid early cooling in Apollo samples 76535. And while he's setting up his slides, I can try to introduce him. So he's doing his PhD right now in University of Hawaii at Mānoa. He got to Hawaii from University of Colorado at Boulder, where he did a double major in geology and mathematics. And he also worked on some geophysical problems, looking at GIS development and in the laboratory of atmospheric and space physics and so forth. But yeah, we're keen to hear about what is found about the polar rocks. So I see the slides working, so it's all yours, Bill.
Thanks. So I'm excited to talk to you guys today about some research we've been doing on Apollo sample 76535 and our attempts to understand its thermal history through diffusion chronometry. So our understanding of lunar geology is, of course, based off a variety of methods, but key among them is our returned samples, what actual rocks we possess from the moon. And of those, the majority come from the Apollo suite. And so this sort of a variety of rock samples and interestingly different geology from Earth has led to a generally accepted hypothesis for lunar formation in the lunar magma ocean. So this is just the idea that at one point the moon was either wholly or partially molten. And over time, this lunar magma ocean would crystallize, first putting out for the majority of its crystallization would be magnesium-rich cumulates. But as you get to high percent solid, it would start crystallizing anorthite. This would be less dense than their surrounding melt and rise to the surface, forming an anorthosite crust. As you keep crystallizing out, the melt, of course, becomes enriched in incompatibles, and this is noted in potassium, rare earth elements, and phosphorus. So we call this a creep enrichment. And this melt, this final last dregs of crystallization is often called the creep, interactions with which can provide that sort of creep enrichment. Then, of course, as you keep crystallizing, you get more and more iron-rich cumulates and even ilmenites, which are going to be more dense than the underlying magnesium-rich cumulates, leading to probably some sort of cumulate overturn, where the positions of magnesium-rich cumulates and iron-rich cumulates swap. So through our understanding of lunar geology, we have an idea of where these geochemical reservoirs may lay, but these kind of key events in lunar history are still poorly constrained. So if we want to understand the timing of all this, we go back to our samples. So to understand how we kind of classify lunar samples, we need to consider a plot like this, where we just plot magnesium number in our mafic minerals versus anorthite number in our plagic clays. When we do this, several clusters kind of pop out, and this is one of the ways that we identify the different lunar suites. And of interest here is that magnesium suite, or MG suite, up in the top right. So as it has some of the most magnesium-rich mafic minerals and most anorthitic plagioclase, this can tell us something about the geochemical reservoirs that must have been involved in its formation. It would probably involve these magnesium-rich cumulates, which would have been the first to crystallize, but would need to be accessible somehow. And it would need to be emplaced as their plutonic rocks in the flotation and orthosite crust, involving both reservoirs. If we look at the bulk chemical composition of the magnesium suite, it's also apparent that this creep signature, enrichments in potassium, phosphorus, and rare earth elements, is present. This would suggest to us that the creep had to have been involved as well somewhere in here. So we can, if we understand the petrogenesis of this suite, we get major constraints on lunar formation as a whole. And specifically the timing. You need a developed creep layer, and perhaps you need a cumulative overturn event or some sort of event that can tap those magnesium-rich cumulates. So this has led to a lot of interest in studying these samples and understanding the petrogenesis of them. So over time, a wide variety of possibilities for petrogenesis have been suggested. So here you can see in this review paper, they highlight 6 different petrogenesis mechanisms, but of course there's even more than that now. But the diversity of them is significant. You can see there's a theory which nowadays is thought to be a large impactor, which would directly mix lunar crustal material, magnesium-rich cumulates, and creep. And in the impact melt sheet, a slow crystallization in a large magma chamber would lead to creation of the suite. You can have extraction of magnesium suite materials deep in the lunar interior through a similar process to like picrites, which would then interact with creep on their ascent, decompressionally melt, and get emplaced into the crust. Or perhaps it's a process of lunar magma overturn, where in the overturn, there's emplacements of magnesium suite and parent material. But this wide variety to me is mostly telling me that there's not enough constraints on these samples. And to fully address which petrogenesis mechanism is most likely, we specifically would be interested in understanding the thermal history of these samples. And for that, a key candidate would be sample 76535. So this is a troctolite made up mostly of plagioclase, olivine, and orthoperoxine that is, as you can see, heavily annealed and was collected by the Apollo 17 mission right on the edge of the lunar highlands at Geology Station 6. What makes the sample so valuable for this study, though, is the pristinity index. That's this column here. And in describing lunar rocks, this is always a key factor. Of course, unlike the Earth, the moon has no atmosphere and has no plate tectonics, or has negligible atmosphere, which leads to everything on the surface being constantly bombarded throughout history. The surface is covered by meters deep regolith of just impact mixed material. And though this causes a physical effect on the rocks, such as the fact that most Apollo samples are actually impact breccias, it also has a chemical effect, which would interfere with any sort of thermal studies. But troctolite 76535 has the highest pristinity index, an almost perfect 9. It is barely impact modified. And that has made it, as it is the most pristine troctolite and one of the most pristine samples returned from the moon at all, it's made it one of the most intensively studied lunar samples. This can range from understandings of lunar magnetism early in the moon's history to how water behaved when we had the emplacement of these suites. But what's relevant for us here is that because of this pristinity, a lot of different radiometric dating systems can be applied to this sample. And with such a precision that it's actually been fit to their closure temperatures, and a cooling path can be plotted through. And what this shows us is that the sample must have undergone an extremely slow cooling history in its subsolidus portion of the cooling history, where these systems can really gauge. This is in agreement with that heavily annealed structure and the common triple junctions that suggest a long, slow annealing cooling history. But what relevant for petrogenesis is not just the subsolidus cooling history, but the magmatic or high temperature cooling history. So projecting that same line upwards, we can see that before we would expect crystallization to start, there's a 100 million year gap, or even more than that, in fact, between that and the Sumerian neodymium age. So this creates an issue as Fahrenheit sample 60025, which is our best constrained sample from the Fahrenheit suite, is expected to crystallize well after this. So we would have a plutonic rock starting crystallization before the crust it would have been placed into, which is clearly not possible. So either one of these cooling histories must be wrong, and an investigation into 76535's cooling history would seem more accessible. But what can actually reach these thermal histories, you might be able to guess from the previous talk in the seminar, is diffusion chronometry. So theoretically, if there exists heterogeneities in the sample, we could model them and extract out our best fit timescale for the creation of those heterogeneities. The only obstacle for this is that in the literature, repetitively, it is stated that this sample is homogeneous in all its major phases. So no heterogeneities to speak of. However, the sample hasn't been intensively studied with modern analytical techniques for a while, and these techniques have improved over time significantly. And with some tweaking of our probe, our microprobe, we were able to extract chemical maps of plagioclase grains under correct conditions that have extremely subtle sodium-calcium diffusion gradients. They appear to be normally zoned and could be suitable for modeling. They seem to have these nice igneous growth phases as so long as they're in another phase, stopping them from annealing into those triple junctions. Note that if there's not this sort of buffering phase surrounding the grain, it would appear that the plagioclase always diffusively homogenizes. So this severely limits how many crystals we can study of plagioclase. So as our group's been doing a lot of work with phosphorus and olivine, the Simplex-17 target, this is a interesting heterogeneity in that it often preserves these sort of skeletal growth patterns. So don't think of these as like an oscillatory zoning, but rather a cross-section of a skeletally zoned mineral, which this seems like a promising system. You have phosphorus being a relatively slow diffuser, so it's possible it could survive. However, some gabbros have been mapped, which would have a much shorter history than Troctolite 76535 is reported to have. And they were already fairly diffuse with respect to phosphorus. So it's a bit of a long shot, but we decided to map it. And when we did, we obviously found significant and dramatic heterogeneities. So here we have kind of two overview maps with inset maps. So what we found is that not only are these heterogeneities sharp and well preserved, but as we zoomed in, many of them just kept getting sharper, suggesting extremely thin heterogeneities, which would be difficult to explain with this long, protracted 100 million year cooling timescale, during which phosphorus diffusion would be open. So with that in hand, that kind of gives us the idea that we're going to, if we do any diffusion modeling on the sample whatsoever, we're probably going to get much faster diffusion timescales than currently reported. To try to be conservative with this then, we decided not to try to just recreate the cooling path of Troctolite 76535, but instead do everything in our power to maximize the diffusion cooling timescale. So try to get an upper bound for just how long, theoretically, if all conditions are right, these heterogeneities can survive in this temperature history. So we set up our initial distributions with that in mind, trying for thin initial conditions and low diffusive gradients to minimize that driving force and make diffusion take as long as possible. And you can see here that some of those heterogeneities I instead modeled with many thin heterogeneities, which would then need to diffuse together, further lengthening timescale. And of course, I'm sure you're all familiar with diffusion chronometry, but we're just trying to get to the point where when modeling, our heterogeneities approximately match or reach that minimum deviation from the observed current distributions. So to try to constrain this, instead of just saying I can put any thermal history in here, because of course, as any of you would know, temperature is one of the main controls that you can put on diffusive speed. And of course, I need some sort of control on what cooling paths are actually allowed. So I'm going to attempt to make any thermal profiles I come up with smoothly transition into have between 800 and 900 degrees C, and our final cooling rate be around 3.9 degrees per million years within error of this line here. So for our first profile, of course, the common sense thing to check would be just the same line that keeps the same slope. And also linear cooling is going to be a lot easier. And if I do that, however, I reach complete diffusive homogenization. So not just hitting that minimum deviation, but completely homogenizing our plagioclase grains before they fall a full degree Celsius. And similarly speaking for olivine grains, which, given that we need to get to at least 900 degrees C, where this cooling path is obviously in no way compatible with the heterogeneities we observe. So we need to consider nonlinear cooling paths. And of course, this kind of opens Pandora's box a little bit, right? You can draw any sort of cooling path. But if we actually think about our goals here in maximizing timescale, we can really pare that down. So here are 3 example functions. And one of the first ones that I at least thought of is a exponential cooling rate. So what this ends up doing in effect is dwelling at high temperatures and quickly quenching to that right temperature and cooling rate. The problem with this is, of course, that dwelling at high temperatures portion. That's going to cause diffusion to occur extremely quickly and thus minimize our time scale. So the inverse of this equation, a logarithmic cooling rate, it seems more favorable. It quickly quenches to low temperatures and then dwells there where diffusion occurs slowest. This should theoretically maximize our diffusive timescales. So I pared down our set of possible equations to one family of equations, this logarithmic cooling history. You might notice a problem here still, though. This still represents infinite equations. We have these two coefficients, A and B. Note this +1 is just to ensure that at time equals 0, temperature is our initial temperature. So it's just simple logarithmic equation. But we need to find coefficients on here for just a single pair of coefficients that hit that 800, 900 degrees target, have as a final cooling rate of 3.9 degrees Celsius per million years, and maximizes the cooling timescale. So not just any that fit those first two requirements. And to walk you through in a somewhat timely manner how I searched for these coefficients, I'll walk you through an example. So I'll be showing the steps for a model of the phosphorus heterogeneities in slide 46. So the first step in searching for our A and B coefficients is to create a grid. These might look like vertical lines. They're just a series of points, 1,000 points arrayed in a grid from 0 to 10. And at each one of these points, we're going to complete the entire diffusion chronometry model. So we're going to try to find that minimum RMSD and what the final temperature and final change in temperature is at minimum RMSD. So on the slides, change in temperature is referred to as DT. And then we can pull out that A and B term and plot that, temperature versus A and B. And as we do this many, many times over that whole grid, you'll see that these single points become surfaces. And we basically want, as we're looking at these surfaces, to intersect these two gray planes. Those represent our appropriate final solutions to smoothly transition into the subsolidus cooling history. And we can see here that they're both too high, change in temperature, and they're both decreasing with decreasing A and B. So we want to look at smaller A and Bs with our next set of points. So we create another grid, add smaller A and Bs, and repeat the same process, modeling many, many times and seeing where the planes intersect these the appropriate solutions, and then masking out places where temperature is too low, too high, or change in temperature is too low and too high. So theoretically then on these lines, anywhere between these two lines fit their respective boundary conditions that would transition smoothly. But we need the intersection of these two where both are intersecting their planes. And this can dictate where we'll search next. And here, that's this smaller region. When we model this, we get another set of planes. And you can see we kind of just go through this iteratively. This is extremely computationally intensive, obviously, as we're doing, in the end, millions of diffusion models. But we're just trying to get to a point where we have a region of intersection where both these planes are correct solutions at the right period of time. Note this won't give a single final solution, but as you can see, and this next one, we'll kind of get a zone that will want to constrain with these fine vertical lines to try to find a good solutions in the center and bad solutions on the outside to define an entire region. But of course, since that is a region of good A and B values, theoretically anything in there is a good fit. So we're then going to take the maximum cooling time within that region. Luckily, it behaves consistently with A and B, so this is actually quite easy to do, and use that to represent our diffusion timescale. So when we do this, we get significantly slower timescales. So remember, we did everything we could to maximize these timescales. And in plagioclase, to preserve this one grain, we can't have diffusion occurring for any longer than 20 million years. And in olivine, there's a little bit more complicated of a story. I'm not going to try to get diverted by this too long, but I'm sure you guys will hear me talk about this in the future. The diffusivity of phosphorus, when applied to these models, returned timescales that are very inconsistent with plagioclase, much less than a year, which, remember, I'm doing this whole maximization technique. That's a bit shorter than I anticipated. And it's kind of suspiciously fast. Further, we've seen that phosphorus heterogeneities survive in other samples where this diffusivity would suggest that they shouldn't. I think I'll be presenting on Goldschmidt on this whole issue. But for this study, we decided to substitute in the diffusivity of silicon. You see, phosphorus is believed to occupy the same site as silicon, and silicon is an extremely slow diffuser in olivine. So by choosing this value, we're essentially further maximizing the diffusive timescale. The diffusivity of phosphorus is probably faster than that of silicon, even if the currently published value is incorrect. So this 27.1 million years is probably a bit over, but it is now consistent with our plagioclase results, which we feel a bit more confident in. As remember, these are not proposed cooling paths, just like I understand the arrows might be kind of misleading there. They're maximum cooling histories, so anything to the right of this region would be consistent with our modeling results. So what does this actually mean for the petrogenesis of the magnesium suite, that big lunar story I was talking about earlier? Well, you might have noticed something similar between all of these models. It's been historically considered that the magnesium suite is a series of cumulates. I mean, it's dunites, troctolites, and norites and gabronorites. So it's been largely assumed that a very large, slowly cooling magma chamber fractionally crystallized and produced the magnesium suite. However, when I run thermal models based on our diffusion models, I get that any magma chamber to produce troctolite 76535, at least, couldn't be very big. So using the most likely crustal temperature, we get a magma chamber no bigger than 4 kilometers for 76535 to form. Of course, we can increase the size a little bit by lowering the crustal temperature below that, which is currently believed. But even at extremely cool temperatures, that's still no more than 11 kilometers in radius. So what this tells me is that we might want to look for petrogenesis mechanisms that do not require a large, slowly cooling magma chamber. And a hint for this petrogenesis is given in these phosphorus maps, where there's these sharp truncations between phosphorus-rich regions and phosphorus-poor regions, suggesting some sort of dissolution and recrystallization event occurred in their history. A more complicated crystal history than a magma chamber would be likely to provide. Note this is in all phosphorus heterogeneities we observe some sort of truncation. And if we look back on Earth at troctolites that occur here, not all of them form by cumulate processes. So olivine-rich troglodytes from the Atlantis Massif are extremely similar texturally to 76535, down to also having heterogeneities, though amusingly more diffuse than our samples. But these aren't believed to form by a large, slowly cooling magma chamber. Rather, the general consensus seemed to be that a process called reactive melt infiltration, where a melt that is corrosive to certain phases intrudes, dissolves them, and then recrystallizes other phases, here turning one rock type into another. So theoretically, we are interested in pursuing the possibility of the magnesium sweep forming from a similar process. Of course, with those igneous growth facets in the plagioclase crystals, it seems likely that initial crystallization would occur from a melt. But then we can have a mostly solid state system that has melt infiltrating and reacting, recreating the same textures we see today, while better fitting the cooling history that 76535 preserves. So in conclusion, we found heterogeneities in 76535, a sample that was previously considered homogeneous. These heterogeneities, even after every attempt to maximize diffusive timescales, are extremely rapid, shorter than 20 million years compared to the previously suggested 100 million, greater than 100 million year timescale. And these short cooling timescales and dissolution, recrystallization, and evidence from terrestrial samples might suggest that reactive infiltration could be an important petrogenesis mechanism in the magnesium sweep. And thank you. I'd be happy to take any questions.
Thank you, Will. That's many set of very intriguing ideas that you've put forward, and there's new thoughts on the evolution of lunar rocks. And we'll take questions. So once again, you can type things into the chat or ask questions here, speak up on the things. Give people maybe a minute to gather their thoughts. And I'd like to remind everybody that once we have discussed a few things about Will's talk, we'll be discussing both of the talks. If you have questions on either one of the talks, you're welcome to bring those up now. So I just ask one quick thing. So what diffusion coefficients did you use for the plagioclase? I didn't get that.
Oh, I actually used the Grove et al. Diffusion coefficient. So the summary you wrote, I took the diffusion coefficients first, sodium, calcium from there.
Okay. And so is there a possibility that under some circumstances, so people have talked about the effect of water, which I guess is not so important for the moon, but there are things like silica activity and other things which might enhance diffusivity. Would that affect any of your results if that were to be like that? I mean, we don't know much about those data beyond Grove et al. But if new data were to become available.
Yeah, I mean, of course, yeah, changing the diffusivity would change our results. But from what I understand, it would mostly serve, because this is a relatively silica poor system, it would serve to speed up our diffusion results. Thus, our maximum timescales would still kind of stand. Further, of course, we're dealing with extremely long timescales here, 20 million years for diffusion chronometry. That's usually a bit longer than people usually run it for. So actually, the small changes in diffusivity we found didn't affect it as much as, of course, with the phosphorus silicon diffusivity change. Of course, that's multiple orders of magnitude, and that's corresponded to multiple orders of magnitude of change in our timescales.
Mm-hmm. Okay. So then we do get, I mean, this is probably a good point to bring in, because I hear this word diffusion chronometry, and there's actually a Wikipedia page that says diffusion chronometry is more for igneous things, and there's this geospeedometry, which is for metamorphic things, and I don't know where that distinction comes from. To me, they're using diffusion models to get timescales, and if you look at that, then in metamorphic systems, you do look at millions of years, maybe not 20, but you do look at millions of years. So, but that's, it is very intriguing that with the newer analytical tools, we're finding more irregularities, and we can go and have a go at them the way you're doing.
Mm-hmm. Yeah.
So don't see any questions coming up, or there's something here from Martin, but that's for Corliss. If there are any questions here. The other thing, if people are thinking about questions, the other thing I was wondering while you were running through your models was, in all of those things that you're doing, you're assuming there's some kind of a continuous cooling history. And why would that have to be the case? If you have pulses, if you have an impact and a cooling event heating up again, and a non-continuous cooling history, how would that affect any of your results or your models?
Yes. So actually, I spent quite a bit of time thinking about that, because I agree, it's quite plausible that there's not a continuous cooling history. However, what I'm basically trying to model here is just the maximum amount of time those heterogeneities could survive while their given system is open. So if it reheats again at a later date to back above opening, that's actually going to decrease our minimum timescale again. So, sorry, our maximum time scale again. So that actually would kind of work in our favor of shortening time scales if it had to undergo any sort of reheating events later in its history.
Well, if you have a pulse history that right away, of course, by definition, contradicts a very slow cooling history. But what that might do is, allow you to get to much longer timescales, because you'll be holding the thing at a lower temperature for longer, and then just go to high temperatures only for short pulses.
Yeah, but remember that we were already trying to hold our temperature like right above diffusive closure. Like if you look at the actual results, you end up always at the minimum temperature at 800 degrees C, and kind of at that slowest possible cooling rate, staying at lowest possible temperatures. So if it's going to reheat again above diffusive closure, it's already going to speed it up, as we're already trying to remain at the lowest possible temperature, just with the shortest possible cooling from that initially high temperature that it would have had to form at.
Mm-hmm. Yeah. Are we losing you? No, you're there. Did you get interrupted, or did you stop?
Oh, did I get interrupted? I was just saying that we know that it had to start at that higher temperature, but we just modeled to quickly drop to lower temperatures and dwell there. So any reheating events would bring it back above that low dwell temperature and speed up diffusion timescales.
Mm-hmm. Yeah. Okay, so I don't see any other questions coming in for you here. So I have a comment from Martin to Corliss, which Corliss has also responded to, so he asked, he said it was a nice talk, and well, I guess the chat has gone to everybody, but I'll just read it out nevertheless. Regarding the best fits for the chemical and iron isotope diffusion profiles that you showed, option 2, have you assumed a linearly changing composition of the crystal rim in your model, or some form of non-linear cooling history? So Corliss said she did assume a linearly cooling system. So that's actually one of the nicer things that comes out of both of these talks today. I think that you can see the range of possibilities that you can explore with your numerical models. If you can think of a scenario, you can go and try it out and see what it does to your diffusion models. And explore the consequences. So that's what I have here. I am not seeing, I'll give people just a minute to see if there are anything else coming in, either in the chat or somebody shows up to ask a question. Don't see anybody here, so I'll just thank Corliss and Will again for getting up early and letting us have an insight into their work and explaining some of these things very nicely. And I'll tell all of you, thank you for joining in from various parts of the world, as I've been seeing. We will be back again on the 4th Thursday of February. We have 2 talks lined up and we will announce them very soon. And this will continue on every 4th Thursdays. If you're not on the mailing list, if you want to be, do make sure you do that. And you do want to register for every single talk. That's something we do for security on the Zoom platform. So many of you have assumed in the past that if you have registered once, you'd be able to get in and join whenever you want to. So that's just something you need to keep in mind. You just have to, it's a couple of clicks, but you do have to go in and register every time you attend one of these talks. So we look forward to seeing all of you again in a month's time. And in the meantime, have a good day and stay healthy. And thanks, Corliss and Will, once again. Okay.
Thanks
Bye-bye,
for
everybody.
inviting. Bye.